I am really happy to welcome you to the 2023 Hoyt C. Hottel Lectureship. It's my great pleasure to first give you a little bit of an introduction to who Hoyt Hottel was and how this lectureship came to be, and then to introduce our esteemed speaker. Now, Hoyt Hottel was actually a professor here at MIT. He came to MIT from Indiana in 1922 at the age of 19, having just gotten a bachelor's degree in chemistry from Indiana University. He then went on to go through our educational programs. He got a master's in chemical engineering in 1924, working with Walt Whitman. He was actually an assistant director for the practice school at the Buffalo, what was then the Buffalo station. And he became a professor of fuel engineering in 1941. In 1928. In 1941, he became the professor of fuel engineering, and in 1965, he became the first Carbon P. Dubs professor of chemical engineering. And he held that until his retirement in 1968 when he became professor emeritus. Hoyt Hottel actually remained active in our department until his death in 1998. He was a central figure at MIT, particularly in the Department of Chemical Engineering, for over 75 years. Now, he's remembered for his intensity, his intellect, and integrity. His lectures aim to make students think. Professor Hottel made seminal contributions to the measurement of gas emissivity. He established the mathematical framework for the quantitative treatment of furnaces, the first systematic investigation of the laminar to turbulent transition and diffusion flames, and explored heterogeneous combustion. Professor Hottel was also co-founder with Bernard Lewis and A.J. Narad of the Combustion Institute. He was elected a member of the National Academy of Science in 1963, the National Academy of Engineering in 1974, and the American Academy of Arts and Sciences. His professional awards include the United States Medal of Merit, the Founders Award in the National Academy of Engineering, the Founders Award in AICHE, and the William H. Walker Award in AICHE. That is a short list of many others. And just a little bit of fun facts about Professor Hottel is that he was engaged in solar from the very beginning. This is an example of a solar energy house that he was a part of designing back in 1939. His broad interest in energy is still very relevant to today's energy, sustainability, and climate discussions. He actually had funding from the Godfrey L. Cabot, which allowed him to build this house and to do further studies that led to the choice of a flat plate collector as the most promising device for solar heating, and construction of the first solar heated house, along with 3 others, which provided data for economic assessment of solar space heating and hot water supply. Professor Hottel advocated for the logical assessment of the economic use of the sun as an energy source. And it's with that spirit that I introduce Professor Peter Green, who is the Deputy Laboratory Director for Science and Technology and the Chief Research Officer for the National Renewable Energy Lab, or NREL. So a little bit about Peter. He is actually shown here in his NREL role. For example, NREL has a huge role in advancing renewable energy across the nation. This is one example in which he is present in the signing of an Australia-United States Net Zero Technology Acceleration Partnership at the Sydney Energy Forum. And you can see him here with our U.S. Secretary of Energy, Jennifer Granholm, and Australia's Minister for Climate Change and Energy, Chris Bruin. Now, Peter was born in Jamaica and moved to the United States in 1977. He attended Hunter College, graduating with his bachelor's and master's degrees in physics in 1981, and went on to Cornell, where he received his master's in 1983 and a PhD in materials science and engineering in 1985. Prior to his appointment at NREL, Peter spent 20 years on the faculties of the University of Michigan, the University of Texas at Austin, and at U of M, Michigan, he was the Gorgu's Endowed Professor of Engineering, professor and chair of materials science and engineering. So he and I share the chaired experience, and professor of chemical engineering and of the macromolecular science and engineering groups. The research conducted in Professor Green's lab at that time was devoted to developing a fundamental understanding of and controlling of the structure and properties of soft materials for applications that include energy conversion, active and passive coatings, membranes, sensors, and organic, electronic, and electrorheology. He served at that time as director of the Energy Frontiers Research Center, or EFRC, the Center for Solar and Thermal Energy Conversion, housed at the University of Michigan and funded by the U.S. Department of Energy. The research center works to explore novel materials that will more efficiently convert solar energy to electricity. At the University of Texas at Austin, he was professor of chemical engineering and the B.F. Goodrich Endowed Professor of Materials Engineering. And he began his professional career at Sandia National Labs, where he spent 11 years. Now, Peter Green is a former president of the Materials Research Society. He's a former member of the board on physics and astronomy, that is the National Academies Board, and a former member of the visiting committee for advanced technology for the National Institute of Standards and Technology. He was the inaugural editor-in-chief of MRS Communications and is a former divisional associate editor for Physical Review Letters. He was recognized with Secretary of Energy's Achievement Awards in 2020 and 2023. He is a fellow of the American Physical Society, the Royal Society of Chemistry, the American Ceramic Society, and the American Association of Arts and Science, and the MRS. He was recognized as a distinguished alumnus of the Materials Science and Engineering Department of Cornell. Here we see a picture of him speaking at Cornell as an alum. And he has very recently become a member of the National Academy of Engineering. And with that, I am very happy to congratulate and welcome Peter this session.
Thank you, Paula. And good afternoon, everyone. I'm delighted to be here, and thank you all for inviting me for this lecture. Am I seeing anything here? Let's try.
Oh, it's not showing.
I should mention, so the very first department colloquium I ever gave was in this department in 1986, just after I finished my PhD. Alan Hatton, I remember talking to him, reminding him. So I just thought I'd share that with you, sort of exciting time for me. Thanks for that very kind introduction, Paula. So as the greenhouse gas emissions continue to increase rapidly globally, the climate crisis evolves and unfolds with pretty important consequences. And so it's really important that we think about a future energy system that's functional enough to begin to address some of these challenges. Also to begin to serve customers in very, very diverse communities, from big cities across to even rural places that ultimately have to partake in this transition as we get towards a low carbon economy. And that's sort of, in a sense, a summary of my talk. And maybe one of the big messages from this is more than just technology advances, but there's a very important social aspect of this to ensure that everybody becomes a part of the solution. Otherwise, it's really not solved, essentially. So as Paula mentioned, I'm currently at the National Renewable Energy Laboratory, NREL. It's a lab that was formed in 1977, right at the end of the energy crisis. Initial work was on solar energy. And at that point, the DNA of the lab formed in the sense that there was foundational work, but at the same time, the researchers had to connect with industry for potential markets. Otherwise, they were going to be not allowed to exist. But that really shapes the way that the lab is engaged in research with partners and partnerships in everything that we do. We're a DOE lab that's what's referred to an applied lab, where we do foundational work with the intent of potential technologies and markets. It's fundamentally different from, say, Lawrence Berkeley or Fermi Labs, where there's a lot of discovery science, as an example. Just to let you know. The other labs, for example, you have the NNSA labs like Los Alamos, the bomb, for example. That's so the labs have very different, I would say, missions. And so for us, it's renewable energy. but largely evolving around this energy transition. So we have partners who work with all the labs together, and that's maybe one of the key things to let you know. So later on, we began wind energy became a part of the lab. And so if you look at the modern day designs of wind blades and control systems, that came from NREL working with partners like GE and Siemens. It's a lab that works on water, wave power. There's a lot of engaging that with both the technology and the science. And geothermal energy is another area. It's a lab where you find people working on doctoral dissertations across the board, to people from industry embedded with us, depending on it is what we're working on. Another area of interest to us is bioenergy. Again, there's large emphasis currently is conversion of biomass to chemicals and fuels, as one example. Fuel cells, we've been doing hydrogen for a long time, for at least 20 years, both the production, storage, transportation, as well as its applications. Transportation of build is a big thing. For example, the electric charging infrastructure, a lot of analysis was done at NREL as an example, things that we do. So there's a lot of techno-economic analysis on LCAs that we do. Buildings, the world's first office net zero building came from NREL. There's a lot of research in buildings, buildings of the future. I'll say a few more words about that soon. And over here, we think about the grid modernization, the hint. The labs, DOE's invested tens of millions of dollars in trying to modernize the grid. It's a process that started trying to recognize that the way people use energy with various energy technologies is changing, and we need to be thinking about a resilient grid, energy grid of the future. There's also the systems engineering, another big area. We have very unique facilities, which I'll talk about very soon, where we can look at configuring all forms of potential energy grids to understand interoperability of devices, as an example. So we're a lab, we're about 3,700 people. 2015, the lab had a new director, Martin Keller. We were around 1,700 people then, just to give you a sense of how much we've grown. And so we have a little over 200 postdocs, as an example, a lot of grad students. We also have a lot of faculty who have joined appointments from universities with us as well. Another key thing is that we have about over 1,000 partnerships, from small towns, from the city of LA, where we've helped them think carefully about how to get to 100% renewables, to countries across the globe, to very, very small communities in Alaska and places like that, as an example. I'll say some more about that soon. We're essentially on, I thought I'd change that. We're 3 campuses. There is one in Golden, Colorado, another one in Boulder, and in Fairbanks, Alaska, where we're looking at extreme housing weather events, all right? So, what's the challenge? Just to remind you of the challenge. I think we all know about this, but it's worth emphasizing a few things. The warming of the planet is really responsible for a lot of the extreme weather events. There's no question about that anymore. And just to look at some raw data, 1980, a couple of $1 billion weather events. 2023 right now, there've already been 23 of them so far, as an example. The cost is huge. And so if you look across to the left, the temperatures are up everywhere. Precipitation is up everywhere. And so these are new challenges for us to force us now to think about adaptation. We're never going back to what it was in 1920, 30, 40, 50 to 80. That's something to bear in mind. And of course, so we need to be thinking carefully about, as we process materials and the emissions. As chemies, you guys know, really think process heat is probably not the best way to do things. And some of you are already thinking about electrochemical processes as ways to do things, but the progress won't be rapid enough, I don't think. There's also the challenge of cyberware, cyber criminals. You see it more and more. So if you're building a new energy system, which is going to be more highly distributed in terms of energy resources, you got all kinds of digital interfaces. Each digital interface is an invitation to cyber criminals. So that's a new area of research that we have to think really, really carefully about. And of course, plastics. I don't want to complain about plastics, but the thing is, a colleague of mine pointed out to me, if you look at all the plastics in a landfill, it weighs more than all the humans on the planet. And that's just a given. Just like every year, the amount of greenhouse gas emissions at weight is more than the cumulative weight of all humans, by the way. So I don't have to tell you more than that to give you a sense of the challenge that we face overall. We understand quite well that electricity and heat, transportations, buildings, manufacturing, those are some of the key some of the key sectors where the emissions are huge, and certainly processing of materials. And so this becomes a part of how these become data or information that we use to think about what problems we have to solve. Now, the decarbonization challenge is central to this, right? And so if you talk to a lot of experts who think very carefully about these questions, the idea is that you want to electrify all end-use technologies. That's the first thing. The second thing you want to be able to do is you want to be able to have a low carbon emission. So you're ultimately trying to get the most renewables and nuclear. Don't want to forget nuclear as part of it. The system has to be resilient. And that's another argument for using a lot of distributed energy sources for generation. The grid of Edison was built where you're generating these centrally. And you don't want to do that anymore. And so in terms of just trying to harden the grid, that becomes important. Carbon capture, we want to escape that, and storage is going to be really important. Of course, we're going to have to pull carbon, CO2 out of the air. There's no way around that. And yes, we're looking for a lot of low temperature, low pressure projects, processes for producing the materials where we reduce emissions. So in a sense, we know what to do. I mean, that's the good news. But there are lots of factors that can tend to slow things down. I just want to give you a sense of how quickly we've begun to adopt renewables, say in the US. So we're about 25% of renewables that contribute towards electricity in the country. That number is going to have to go up much more rapidly, but at least it's a good start. And perhaps maybe a way of maybe quantifying this a bit more is that if you just look at the cost of wind wind and the cost of solar dropping significantly, and EV battery costs are all dropping. And certainly with that, you're beginning to see a lot more uptake in these technologies. And so the reduction in price of renewables is actually a good thing because it gives us some confidence now that a grid powered by renewable sources could be affordable. And the cost of renewables is comparable to all the conventional resources all over the world, in some cases much cheaper, and will continue to get cheaper with time. So at NREL, I mentioned to you, I gave you a summary of the things that we've been doing over periods of many, many years. We're going to ask a question 2016-17 after Martin Keller became the director, and he had a new leadership group. What is the long-term value proposition of the lab? Based largely on things that we do really, really well. And so one of the things that struck us is we went back and we looked at all those trends that I summarized for you before, and asked ourselves, how do we plan for the future to ensure that we're relevant? And we decided that there were going to be 3 strategic directions. The first of which, and I'll get to this right now, is we call this integrated energy pathways. And this was with the last administrations that they had a discussion with them about, let's think about technologies. And the question then is, envisioning this new grid, where are you going to couple energy transport in all the major sectors, transportations, buildings, electricity, and things like that. That was the first thing. And then the question is, what are some of the key questions, technical questions that need to be answered in order to enable us to look at that? That's what we did. And it's important to let you know that we weren't sitting by ourselves. We have about 1,000 partners. We're engaging a lot of partners from around the country, industry, utilities, spending a lot of time with us. One of the things we recognized from this new grid is that, if you imagine us cities of, say, 1 million homes, for example, you could have power generation by rooftop solar, storage, smart devices, EV, things like that. Essentially, what you have are millions of distributed energy resources. That's going to happen eventually, and you can no longer manage your grid. Humans can no longer do this. It's going to be done autonomously. So we're engaged in the process of doing a lot of software development with a lot of partners. We spend a lot of time with people from utilities industry, from everywhere, sitting together sometimes a week at a time, identifying what needs to be done and how we're going to proceed. And so that was the key thing. The second part of it, we call electrons and molecules. Europeans call it power to X, but we began this 5 years ago. The idea is that you can use electrons from wind, solar, converted to chemical bonds, either for storage of chemicals or to drive reactions, electrochemical reactions, for example. And so that's another aspect of it. And you can take advantage of CO2 or nitrogen And it can produce a lot of things that all get good chemies now. Question is, can we do that at scale? The third area gets back to this sort of circular economy question, in that you want to be able to reuse, repurpose, or recycle. You want to design things for recycling. And so if you look at wind blades, for example, there's now a lot of this work done to, instead of making wind blades out of thermosetting polymers, we make them out of thermoplastics, which are easily recyclable. We've done this, working with industry. DOE supported NREL, other labs, industry, and academics to do that. And it's actually sort of going commercial soon. And that first blade that was made 13 meters is actually on its way to the Smithsonian, as an example. We're looking at recycling of modules, of solar modules, for example. But we're also looking at extending a lifetime. 5 years ago, a lifetime was like 15 years. Now we're at 35 years, as an example. The recycling of plastics, things like that, or upcycling is a big thing now. Some of you guys are doing it's a big program at NREL. So these three areas encompass the direction in which the lab's going at this point. So I mentioned to you this future energy system. So here are the thoughts. The idea is that, one, it's going to have to be resilient, and it's going to have to be physically and cyber secure. Secondly, it's going to be mostly wind and solar. And all the analysis we're looking at, and I'll show you some data later on, wind and solar are going to be key things. Yes, there's going to be geothermal and nuclear, and there's going to be some natural gas. And I want to be clear, we're going to be burning fossils for a few years to come, because there is no switch to turn on or off. But the idea is to simply get to the stage where we're a decarbonized system. I mentioned electrification being key. The buildings of the future are going to be grid interactive. Walmart's got its electric charging system, for example. It's going to do what it always does for its customers, and it's going to be able to have two-way flow, all kinds of sensors, as an example. The processes, again, decarbonizing industrial processes. We're actually now gearing up at NREL to look at the decarbonization of steel, something we haven't worked in before. But then we're working in new areas. And perhaps the thing to emphasize here is that during our planning, we looked at key areas of investments, and we identified key areas of investments by putting together workshops and inviting some of your colleagues here who became part of it to decide where the investment should be. And so we made investments of millions of dollars on our own. For example, this idea of an autonomous controlled grid. There's a lot of investments, millions of dollars went in there initially to do a lot of software development. A lot of it's already happened. And by doing that, we've attracted sometimes 5 times more money because of industry coming to work with us. And it also meant we hired experts in areas that weren't there before to complement the skill sets that we have. That was also part of what we did. Then, of course, there's the transportation. And we know about electrification of sort of light-duty vehicles. Heavy-duty trucks are likely going to be fuel cells. And certainly, we're thinking of low-carbon fuels as well. I mentioned communities down here because in the old days, when we worked with a community that wanted to get some sort of renewable energy generation, the answer would be, oh, here's a wind turbine, or here's a solar farm. This is good for you. We're a little more intelligent now, because you need to find solutions that are unique to the community, that meet their needs. And we'll talk some more about that. And it meant spending time with people and understanding what it is that they're doing so that you can understand how to help. Otherwise, you've been wasting your time. So buildings, just by way of context, use most of the electricity in the country and gives off a lot of CO2 here as well. And as we're thinking about the buildings in the future, then again, these are the things, right? You're looking at decarbonizing things. You're going to have to do improvements in the thermal envelopes of buildings, and there's going to be a lot of renovations of homes. DOE is spending a lot of money on that, by the way. Electric heat pumps are going to be important. But electric heat pumps, just to emphasize, they work well in environments as well, well-built buildings, places. If you have a leaky infrastructure, that's a problem. And so there is a lot more work that needs to go into this. Initially, many people were thinking you have a technology like a heat pump is going to work, everybody does. But once things are out in the field, you understand quite well that a lot more work needs to be done. And so we're at that stage. Our lab, for example, is hiring more sociologists and economists before. There's an equity part of the lab that didn't exist before. These are really, really important parts of trying to address the solution. But so these buildings of the future, then, they're going to be grid interactive, generate power, store, two-way sensors. You're going to have occupancy sensing, smart buildings. And as I show you this, their facilities at NREL, we can actually put things together to understand the interoperability of all these technologies in one place. That's a pretty common thing. Utility has a new inverter, they have no idea how it's going to work. And they don't want to put it in the field. They can come to NREL and do a hardware-in-a-loop experiment to get a lot of data before they put this out there. So all of these things are possible at the lab right now. We're from, the electrons and molecules initiative I mentioned after the grid. The idea then, you're looking at processes where you're looking at sort of solar, wind, and you got molecules you can actually use various kind of processes to get to reaction intermediates. If you get reaction intermediates, you guys know you can make anything after that. But for us, yes, we know a lot of you know how to do this, but can you do it at scale? And that's where the lab's coming. What potential strategies are scalable? And we do this with partners. Here's just an example of CO2. And there are all kinds of CO2 conversion pathways to the fuels and all kinds of chemicals out there. We're looking at all of these, again, with partners, trying to understand how one might do this at scale. Other area is sustainable aviation fuels. There's a whole range of strategies that we're looking at the lab. Those of you who went to the MIT practice school a few years ago, if you're still around, some of you might have graduated. That gives you some idea. There's a lot of strategies of how we're planning to get there, not a single one, by the way. And as I mentioned to you, we're looking at things, getting to things really at scale, where we're looking at renewable feedstocks across here, looking at intermediates, and then ultimately trying to convert them to refinery processable systems. Yes, we have refineries there, and we work at a lot of companies, Chevron, Exxon, places like that, to understand at a smaller scale how well something's going to work. And this is something the lab's been doing forever, for many, many years. So that's perhaps the value proposition of a lab, where we can do things at much higher scale than universities. But then, just by way of context, we publish 500-600 refereed archival papers each year. Almost all of them have academics as co-authors. And then we publish a lot of other reports with raw data that people use that are on the web you can get. And I can track how many of these things are downloaded, and there are like 2,000 of those things are downloaded a day from across the entire globe. So there is value. So we actually, another thing, for example, just as another example, we can make green hydrogen because we have electrolyzers. They're at mega scale electrolyzers. We can get CO2 from basically any source, and we can make synthetic membrane. SoCalGas was the first collaborator a few years ago. Here's the infrastructure down here where we're looking at materials for storage of hydrogen. The hydrogen vehicles across campus. We're actually trying to understand how to fill a hydrogen tank of a truck. Actually, we have the world record. I won't give you the numbers because I'm going to get it wrong, but we do a whole lot world record for doing that as an example. So, just by way of context, you got sort of hydrogen which you can make a lot of ways, the SMR method being the most unfriendly method, but the most popular one out there. But you can look at all the uses, from transportation to synthetic fuels to ammonia. And the idea ultimately is maybe to do ammonia using some kind of process as a way off, rather than the Haber-Bosch process, which of course is incredibly intensive in terms of energy use across the board. The hydrogen hubs that were mentioned, I think this is pretty well known to everybody out there. And the Inflation Reduction Act are also part of trying to get to the goal of $1 per kilogram by 2030. I don't think we're gonna get to $1, but maybe we get to $2, maybe. But at least that's a big improvement. All right. Just to give you a sense, this is another facility at NREL in Boulder. And so this is what we call is a configurable grid interface. And here's the point where you got fuel cell work, you got electrolyzers, you got mega scale solar, more. You got these 3, 4, 5 megawatt wind turbines. And together with this configurable grid interface, we can actually configure any kind of grid that one can envision. It's a 20 megawatt facility. So you're looking at about over 1,000 homes, just equivalently. And we can do experiments and understand all kinds of effects of all kinds of transients, of faults, how they work and how you manage them. We created the conditions that made a mess of the Texas grid a few years ago, for example. It's a way to begin to test out and understand essential interoperability of various devices. If you want to make hydrogen using wind or solar, we do this here. The company is doing that exactly to find us how to do this. This is just a direct air capture. So we're looking at working with this company, a global thermostat. And so that's going to be, that's coming to a facility where we're actually going to be trying to understand how do you connect this with renewable electrons and potentially understand how one might address the CO2 capture and conversion. So at the lab then, just a summary here. There's a foundational research. There's this facility, energy system integration facility. This is, I alluded to this earlier. This is where you're looking at small devices, trying to understand how they operate or they improve. Their utilities spending time here embedded with us looking at, for example, advanced distribution management systems as an example there. This is a new facility right now being built. It's going to be about $250 million. And it's about trying to, as you develop materials for whatever applications, can you get through this valley of death working with industry to scale production? That's what this is going to be about. And so there's a lot of partners that are spending time with us. And then we're going to get over here to this, what we call advanced research for integrated energy systems. And I'll tell you a bit about this for a moment here, because this is really important. Here's a sort of a schematic of it. So here we have the ESIF facility I just showed you a picture of just now. And here is the other facility I showed you with the wind turbines and everything. And so what we have then, we have a high performance computer dedicated to energy research. It's one of the top 20 in the world. And we can literally emulate any particular energy system, right? So at one level, we can use real assets and configure something. But what happens if you have millions of devices? And so we're at a point now where you're basically literally emulating the behavior of these devices to any potential system to give you a sense of how you might build a new energy system, like for an airport. We're doing it with Dallas-Fort Worth, by the way. And so that's why this is going to be really important. This particular system, Aries, I mentioned to you, is an R&D 100 award winner. And I want to give you one example of how this works. So Fairbanks, Alaska. The Electric Association is fairly large. It's mostly fossil powered, and they deal with all kinds of price fluctuations and uncertainty. And what they like to do is they like to retire a coal plant. And so we spent time with them, and we created a digital twin of the energy system. And it's a physics-informed digital twin. So essentially, any transient or anything, this twin reflects it. And so what we can do now is remove the coal plant and put wind and storage and demonstrate how well one can ultimately make that replacement. And so this is just one example of creating a digital twin of an environment before you can make a decision about what works and what doesn't work for the environment. And so that's kind of, that I think is exciting. So for this idea then of working with communities, this is C2C, Clean Energy to Communities, a DOE program investing tens of millions of dollars. And the idea then is that if you want to work with a community about trying to help them achieve clean energy goals, one, you spend time with them to understand what the goals are. Two, you understand what the budgets look like. Three, you want to find solutions that make sense for them. And these solutions are going to make sense to them depending on what the budgets are like or what impact they might have on the community in terms of jobs or what have you. But at least it's a solution that you develop with them collectively and creatively that's going to meet their needs. And that's what this is all about fundamentally. And so that's important. And so the lab, the DOE system is now looking at this, and ENRA leads this in terms of engagement. Puerto Rico, the massive hurricanes that they had, we're spending a lot of time there. The Energy Secretary spends a lot of time there. And they were working in great detail to help them to get to 100% renewables by 2050. And this involves spending a lot of time on understanding not just the electric system, but people's preferences and needs and everything, and trying to design something in a way that they can live with, they can work with, that's sustainable long term. We've worked, just in passing, we've worked with over 2,000 communities over the last many years. So NREL sort of knows these communities, and this is a statement of how well I think if you're really gonna go through this transition, you have to work with communities. So here I'm looking at, so here's an example of another, moving on to scenario planning. The new administration came in and mentioned that they wanted to get to an energy system that's carbon-free by 2035. And that's fine, it's a great goal. And so the question that came up to our folks is, how is this possible? And what are the potential scenarios where you might want to accomplish that? And what it meant then is that they did a lot of very deep analysis. And the first point is that NREL has a great deal of information about the solar resources everywhere across the US and parts of the world, by the way. Wind, same thing. And they have information literally at 5-minute intervals, hours, days, about what the resources look like everywhere. And that's really important because they can know with some of the software, software is all sort of open source. And they can ask the question saying 2050, what do they need to build and where do they need to build, or 2035, and where to build it. The information also includes understanding how people are going to adopt certain technologies, specifically different parts of the US, right? That's involved a lot of agent-based models to understand this, by the way, and surveys. That's really, very, really key. And it also considers areas that are excluded as well to understand this. And it also, the program, this regional energy development system, you can look for this on the web, you can open source, and you can just find a lot about it if you want to play with it. Gives them some insights of what they're going to build and where they're going to build it, as well as what's dispatchable. So it's that level of detail that's involved here. Now, the prediction, no, not prediction, I want to be very careful. They look at scenarios. This is really, really scenarios. And so if by 2035 you want to get to a completely decarbonized energy system, what's important here, they look at the scenario, they might ask themselves, what if you have a case where CCS isn't cost effective, hypothetically, it's all hypothetical. And it predicts if that's the case, what's the minimum, in terms of minimum costs. It's telling you you're gonna have a certain amount of wind or solar, wind being blue, solar being yellow here. And it's also gonna mention natural gas and essentially some level of nuclear, but very small. If on the other hand, it says all the options available. So you're gonna be allowed to build solar and wind anywhere you want. You're gonna have transmission anywhere that you like, and with no barriers in a way that makes sense. Then what you find is that you're probably having to build less capacity. So look at the constrained one, which is probably more likely. One that maybe they limit the amount of wind, limit the amount of solar where you can actually decide things, and that's happening already. And they assume that you can put transmission everywhere, by and large. Then it also projects under these conditions what happens. And what you see, for example, there's more nuclear being produced than you would have expected, and you're doing a lot more storage. So it does tell you what's dispatchable and how much that you need. But maybe the big message from this is that regardless of the scenario, you're gonna need 2 terawatts of wind and solar in the US. That's what it's telling us. And it's also telling us, quite frankly, that by 2035, you're gonna need anywhere between, you're gonna need quite a bit of wind and solar, maybe about the 4, 5, 6 times. Same thing with wind. And you're gonna have to start building very, very quickly. That's what it's really, really telling us. It's also telling us, for example, that nuclear maybe by 2030, you start having to build more. But again, we don't know what the cost of nuclear is gonna be. That's a different story. And but it also shows the rapid drop of fossil at this point. So these are the scenarios that one is being looked at. So there is some guidance in terms of how one might do this. Something else I want to share with you on this front, because there's a study that was done in North American grid with high amounts of renewable power. And the idea is that you have Canada, US, Mexico. Again, a hypothetical question. What if you be able to link transmission and link energy resources and share things? It was done to provide planners, grid planners, policy people industry folks essentially what it might look like. And so this is a case where you have high amounts of wind and solar, and you also are looking at a case where you're also building out. Here you can see the solar being yellow and the blue being wind, and so as the night goes, you start seeing, as night comes on, you see a lot more wind, solar shuts down. And so the idea then is that under these conditions, can you balance supply and demand? Is that going to work? And it tells you, these software programs, the analysis I mentioned to you, tells you exactly where things are going to build and how much you need. That's what this really is getting to. And it provides, for example, all the cost savings that are result, tens of billions of dollars. And it tells you that's quite feasible. So the point here is that the simulations provide some insight in where you build and how you build and whether things are going to work. This is an example of so San Francisco. It's got 4.3 million customers, 20 million controllable devices I mentioned earlier. And so this is a massive complex simulation that we did covering every building load, solar EV chargers, everything across this. And so this massive simulation accounting for all of these assets across San Francisco enables us to do some planning, ask questions about what happens if you start changing things or increasing the amount of sort of generation or storage or what have you. It's a good planning program right now that's being done. Keep it here. I want to say something about the renewable generation. So wind being a key part of it. There's a lot of work that needs to be done on wind. There's a science paper actually talking about you need to optimize the performance of wind farms. That needs to be done. There's also as they're building bigger and bigger wind machines, wind turbines, and either the same. And as you get higher and higher, there's a question about the interaction of the wind blades with the resource. So there's a lot of simulations work done there at very, very sophisticated levels. Trying to optimize the wind farm from a simulation point of view is an exascale computing problem that all the labs are working on collaboratively. Here's just a nice example. You make these wind machines bigger and bigger, then you can capture a much larger part of, if the wind velocity is low, then you can capture more wind. The amount of power you get goes to the square of the velocity, essentially, and the area of air. So that gives you a sense. The biggest wind machines right now are about the size of the Eiffel Tower, by the way. That's kind of what's planned. But, this is nice, but there's work to be done there. Some of the wind companies are having trouble because they're predicting what they can sell wind for, and then with interest rates going up on supply chain things, they're in trouble. But I think the government can fix that. Right? This is a 30-meter wind blade that was made, and this is now scaled to about 50 meters as an example. There, and it's all thermoplastic, working beautifully. It's a composite, in case you wonder why the thermoplastics works like a thermosetting polymer. All right, solar. About a year ago, we hit a cumulative amount of solar of a terawatt. This is really exciting. Those guys are celebrating. Here we look at, for example, if you look at solar as a function of year, the cumulative amount of solar is what it is right now. And as a function of time, if it continues at the rate until 2030, they expect they'll meet this goal of 75 terawatts with this community together as estimated that we will need to get to these decarbonization goals. Here is just different world records of the efficiencies going up. So the cell efficiencies are going up, but they're going up really slowly. But the new technologies, the multi-junction solar cells have really, really high efficiencies, but they're too expensive. You're gonna make them cheap. Places are working on that. Or if you look at the perovskites, could be a godsend, but they're not stable enough. But potentially stability has gone up significantly. 2016, these things wouldn't last more than a few hours. Now they're lasting almost a year. So progress. Never bet against science is my philosophy. All right. There is a lot of stuff out there saying that solar is going to take up so much of the space on the Earth if you want to go the direction of solar. I want to correct that record. If you look at the most efficient solar module right now, and you compare that with basically the available area to put solar cells, it's less than 1%. And you're gonna have solar. It's gonna be agrivoltaics, where you're gonna be putting solar where it's the same place where you measure, where you're planting things that works. We know that works. Or you're looking at things on the river like in Singapore. So there's lots of possibilities here. Just to correct that record. The other thing to let you know There's a lot of discussion about the modules having all kinds of toxic materials, and there's going to be lots of waste out there. Well, guess what? The module life is no longer 10, 15 years. It's like 35 years. The efficiencies are way up. And so the big message then is that this is a better way to see this. If you look at the amount of waste that's coming, municipal waste, or coal ash, right? Look at coal ash. And this is the waste from the solar modules. Okay? The oily sludge from stuff, this is giving you a sense that the waste is not an issue. This is a very quick one just to let you know that factors, we're looking at recycling, and so there's a lot of work looking at social factors, the age-based models to look at social factors in terms of what do people do in terms of recycling and how can you think carefully about collecting them. And so there's a lot of work. This is just to give you a sense of the scope of work that is happening. Hard disk drives, wind blades, PET bottles. There is quite a bit of techno-economic analysis and LCA being done at the lab to guide some of the work that we're doing. The question of geothermal energy always comes up. And so here's an example just showing pictures of the geothermal reserves that are readily available. It's mostly in the West. And so there is the geothermal visual program is basically pointing on by 2050, the idea maybe is to have 60 gigawatts, which is about 8.5% of generation. And this is really important. There are, of course, geothermal heat pumps and there's district heating. These are all key things. But the challenge with geothermal is that you're going to a point maybe 2 miles below the surface of the earth, and the rock is really hard, like 20 times that of cement, and the material, and it's corrosive, and so there is some materials challenges about how one actually does get there. But in terms of the planning and the research that's being done, they project that you should be able to, at some level, get geothermal energy throughout most of the US. And so if this really is going to be that much geothermal, then one of the things that, for example, if you use wind and solar being very variable, I never say intermittent, variable power, very important. The geothermal provides some firm capacity. And if the cost of nuclear becomes effective, I think we're home, essentially. That's what it gets back to. And so I'm optimistic on that front. All right, so here are my last 3 slides, and I kind of wanted to share just a few things with you coming up. And one of them is that if you look at this, there's lots of laws being passed in municipalities across the country to not have wind or not have solar, and that becomes a tricky thing. And if you look at wind in 2018, look, we're in 2022. And so if you go through a point where you start reducing the number of locations where you can site wind or solar, it can have a rather negative effect on us. And so that's something to think about. But then if you have nuclear working by then, everything will sort of work together. But just here we are. The other thing I wanted to share with you is that if you look at the Inflation Reduction Act, I'm not playing politics here, but this is pretty serious stuff. If you look at because of the IRA and deployment, what you see here, if you look at the various technologies up here, and IRA versus no IRA, well, for example, wind, and you look at solar and storage, it accelerates adaptation. So the point then is that it's not just a technology and it's developed and people love it, but you need to provide incentives, tax incentives of people to want to use them, just like they did for other energy sources in the past. That's going to be really important. Eventually they pay for themselves. And that's, I think, one of the really important things. And, quite frankly, as the extreme weather events continue, the costs escalate. And those costs are a lot more. They escalate as we continue burning more and more fossil fuels. And I think that's the thing to bear in mind. And the worry is that we're never going to catch up right now, but hopefully we don't end up in a point where we're sort of in the abyss. That's sort of my worry. So this slide, I want to talk about this because the question comes up about what happens with countries across the globe. And so there is this net zero world initiative that was announced by the Energy Secretary at COP26. And the idea is that the DOE labs and some of the US government agencies have now committed, and the work has begun, to work with some countries around the world, one, to establish clean energy goals towards net zero, and secondly, putting together very detailed plans about how they're going to get there. Thirdly, it's going to work with them to find third-party financing, because one of the problems that you run into, I was in Singapore a couple of weeks ago, people are saying, yeah, we get the energy crisis, but some of the technologies we can't afford. We need help. So that will do that. And then the third point is that it's helping them identify policies that they can implement in order to ensure that they can afford things. So on my very last slide, no, the second to last slide, I just want to give you some assurance of things happening, right? Many of you have heard of the earth shots. I mentioned the hydrogen earth shot, $1 per kilogram by 2030. So there's one for long duration storage for the grid. So you want to essentially reduce the cost. So there are calls out, and there are researchers out there doing things. The carbon negative shot, there's the enhanced geothermal shot to reduce the price by 90% to $45 per megawatt hour. And so that's a goal that's been there. There's offshore wind, trying to reduce the price of offshore wind. The price of offshore wind has reduced significantly. But the thing about offshore wind, you can build these wind machines higher, larger and larger. On land, you can't. You guys know what the reason is? Why you're limited in size? You can't transport them. And the wind resource is much stronger, much better way out at sea. So you're getting a lot, and you can actually produce things like hydrogen a lot cheaper. And so there are projects out there that are started. There's the largest wind farm in the world, for example, was built by Equinor, by the way. That's offside Scotland. But they also want to electrify offshore drilling works, by the way. So there's a trade-off in everything in life, right? And of course, there's the industrial heat shot. You want to reduce the amount of industrial heat that's being used. So let me end by sort of pointing out to you, I think maybe the message here is that this transition is more than just science and technology. It involves a lot of investments from the government, partnerships within the labs. Some of the labs making a lot of investments and elsewhere. You got policy coming in, and yes, you have to implement and adopt things. You got to work with communities to understand how these things are going to work. You're dealing with a lot of these challenges out here in terms of environmental justice. This area is now an academic area with lots of papers being published as people think deeply about these kinds of questions. And so this challenge really does involve a collaboration of everybody, every single person doing their part in a way that we never would have imagined. And a lot of the mistakes, poor infrastructure, weak grids, are going to have to be redone. And all the homes that were poorly built are going to have to basically be dealt with for this challenge. So in a sense, it's a challenge that brings the world together to solve something that we can't solve individually alone. So, well, again, thank you guys for having me.
Well, thank you so much, Peter. Before we move to questions,
Right.
I want to present you with the
wow.
Hottel bowl.
Thank you.
And we will step over here because
Yeah.
our photographer would like for us
Okay.
to show you.
Okay.
Yes. This is a tradition.
Okay.
And
Awesome.
it is a Paul Revere style bowl.
Nice. Very nice.
Yes, which represents New England. And we are going to open up for questions. And I know we have a number. We have microphones on either side. If folks want, we can help to hand off the microphone. If you're in the middle and can't get there, just raise your hand. Yes, we will. There we go.
Thank you very much for your inspiring talks today.
you.
So earlier in your slide, you mentioned briefly about the aircraft fuels. I want to ask, is there any particular reason the NRED is more interested in aircraft fuels?
No, I think it's something that we know how to do, given our history in bioenergy and conversion of biomass. It was a natural direction for us to go in. And the fact that we have pilot plants again, it seemed like a natural thing for us to do. It's pretty consistent with, I think, the strategic directions. Yeah.
Right there. Here we go.
Thank you for your talk. I was wondering if you had any thoughts about like the implementation of the clean hydrogen like credits in the IRA, because I know like right now they're trying to figure out whether like hydrogen made from natural gas with carbon capture should qualify or if it should just be like electrolyzed or hydrogen. So I was wondering if you had like, or you or Enro have thoughts on like what it should be done.
I don't have an opinion on this. I do know that they did do some analysis to understand what the impact would be based on those decisions. And I think if they turn out not to be good, I think DOE will go back and revisit them. This is my take.
Thank you.
Thank you, Professor Green. I'm a PhD candidate working on decarbonizing heavy trucking, and I interacted with a lot of stakeholders that are in the field trying to decarbonize their heavy trucks. And one of the things that I heard the most is that the lack of infrastructure. So one of the things, like other than like just the infrastructure of the grid to recharge the EVs, but also if we do hydrogen trucks, how
Right.
do you get the hydrogen to where the trucks
Right.
are?
Yeah, there's a lot of work to be done there. I totally
Okay.
agree with you. It's still
Okay.
early days. Yeah.
Can you shed some light on like what efforts has been done or planned in the?
I don't know the details. There's a study that's going on right now to better understand how to do this. That's about as much as I know. But the point then is still early days, and I'm pretty confident that
Okay.
they understand the issue. Yeah.
Okay, all right, thanks.
Yeah.
Additional questions? Yes.
Hi, thank you so much for the talk. It might be like not directly related, but you mentioned about the cyber warfare, and also I wondered like with in the progress of technology, there are more and more computational like dependent infrastructure, and I want to know like in terms of energy and thinking about like computations, like the energy using computational related like technology and dependence of societies building on like a more digital worlds like this.
Yeah. Right. So, I mentioned to you that with this new grid, with it being highly distributed, means you have a lot of digital interfaces. There is a lot of work, a lot of algorithms being developed to begin to detect essentially intrusion and to get the point to shut systems down or shut down segments of systems, right? There's that being done. And there's also now beginning to be demonstration on real systems of how well things are working. I can't say more than that, but we're working with a lot of industry together in that area. And so a lot of this, you can imagine a lot of secrets are being kept in terms of how this is done. But the efforts are huge because the consequences are actually quite significant. And we're actually working on building a system and looking at all the potential possibilities of intruders. And so the Aries system, Aries I give an example of, you can put together a digital twin or some system, energy system that you think you want to build, and look at ways to understand how you might protect it from cyber criminals. It's never going to be 100% secure, but at least there's a way to begin to evolve and try and protect it.
Thank you so much
Yeah.
for the talk. What do you think are some of the key mistakes that academics make when they go to engage with industry?
So, all right. So that's more like a personal question. I'll give you a personal answer. Academics fall in love with what they do, and they think they have a great idea, and they go to sell this idea because they think someone's going to fall in love with it. I've made a mistake, but I think what happens, you got to take a lot of time to understand what it is, what the problems are, and where they're going and what they're after, and then begin to suggest what might work. And that's always the best way. At the lab system, it's the same thing by and large. And it just takes a lot of time to understand that, is what it comes down to. Yeah.
Additional questions? Here's one, Chris, right here.
Peter, it was a fantastic talk.
Okay.
I was wondering about kind of critical raw materials and
Yeah.
including water, right? Water is going to be another resource we have to think a lot about
Mhm.
going forward, and electrolysis requires it. So,
Right.
how do we think about that in the context of how much we have to build here?
Yeah. So I know there was a study done on hydrogen, the hydrogen infrastructure, if we get to the point where we're producing so much hydrogen to enable renewables. And they have located regions around the country where potentially they could be building significant amounts, sort of producing significant amounts of hydrogen. And the conclusion is that within the US, it's not an issue from that perspective. And there's another study I looked at in Nature recently that pointed out that in most places around the world, if you have a water scarcity problem, then it's going to get exacerbated. But hydrogen, for example, will not create a water scarcity problem based on analysis that I've seen by and large. Yeah. Okay.
Yes, have it.
Hi, thanks so much for your talk. It was
Yeah.
wonderful. Does the nature of the renewable energy source affect the energy storage, needs in these scenario projections? So, for instance, variable wind might cause you to need a more rapidly, accessible energy storage solution. Yeah.
There's always possible. But I think you can site things, wind and solar, in places where you need to. And the amount of energy storage that I've seen from the analysis, I didn't show that. I'm not sure I showed that to you. It's not significant. Most of the batteries are going to build up for EVs. And that's what's going to drive most of the development. And so as far as the grid's concerned, it's not an issue. You just need longer term storage at a good cost. And yeah.
I had a quick question. Do we have a question already up there? I'll take mine last.
No.
All right. I
Okay.
had a quick question about the siting of for wind and solar, in particular wind.
Yeah.
Are these the sort of like not my neighborhood types of situations, or is it are the siting constraints more related to infrastructure and access?
No, so that's a really good question. And I'm going to give you an answer that you're not expecting. So we know, for example, areas where you can put wind farms and site them, and things are going to work really well because these the analysis we've done takes advantage of looking at terrain, areas, exclusion, everything. And what's really interesting is that I was looking at a survey that pointed out that most people don't have an issue with wind or solar around them. And there is an orchestrated attempt to be pretty aggressive about undermining some of this stuff. So I don't know what the answer is in the end, but that's there. But the other part of it too, there's a lot of work now being looking at long-range transmission lines, right? There is one from the UK to Denmark and to Norway, and that's 500 miles. And there's one being considered from Morocco to the UK. That's 2,400 miles. And so you can actually do this long-range siting, and there's a discussion even among some of the electrical engineers that you can run these things along the state highway or railway lines as a possibility. It's going to be expensive as hell. But, if it comes down to it, there are a lot of ways to do this. And then DOE is now putting together a study to look at regions where the siting of some of these resources and transmission is most valuable. We made that work. And yes, siting and all these regulations slow things down. Again, we're trying to move quickly, but that's another issue by and large. Yeah.
Excellent. One last question.
Hello, thank you for your talk. Well, something that I'm curious about in the simulations for the scenarios, how's the model taking account of the life cycle of these devices like batteries or solar panels? Are we assuming that in, 10 years we'll have a technology that
so I
recycles the
can't answer
material?
that question specifically,
Mhm.
but you can actually Google and see where things are. But yeah, I don't know exactly by and large. But I do know oftentimes when they do these scenario analysis, they do take advantage. They do look carefully at what it costs to maintain things over a certain lifetime. The ones that I'm familiar with, they do this. So but yeah, you can look at Reed's Google, and it has a whole menu of things to pull across to look at. Yeah.
Thank you.
Yeah.
All right. Well, let's
Okay.
thank Peter one last time.
Thank you.
Thank you.